In this video, we're going to begin Chapter 7 and look at Section 1, Planetary Motion and Gravitation. And the main idea of this section is that the gravitational force between two objects is proportional to the product of their masses divided by the square of the distance between them. A few essential questions we're going to answer is what is the relationship between planets' orbital radius and period, what is Newton's law of universal gravitation and how does it relate to Kepler's laws, and why was Cavendish's investigation important? We're going to do this by looking at Newton's third law again and reviewing a couple of ideas there, but also we're going to bring in this new guy, Kepler, and his laws and what he did with planetary motion. Talk about a gravitational force and a law of universal gravitation, so not just the gravitational force on Earth. So if we look at Kepler's first law of motion, Kepler stated that all orbits, planetary orbits, are in an elliptical shape, where the sun is at one of the foci of that ellipse. And so we think of the orbits as being circular, but they're actually elliptical. And all of our planets revolve around the sun in this fashion. Now, some of their ellipses are a little differently shaped than others in that they have a bigger eccentricity. And even just like planets, even comets do the same thing. And so we have comets with short periods and long period comets. And we typically say that those comets, the short periods are less than 200 years and the long periods are greater than 200 years. But all of these objects that revolve around the sun do so in elliptical paths. In Kepler's second law, Kepler noticed that when he observed planets as they revolved around the sun, he found that they moved faster as they got closer to the sun, and then they moved more slowly as they got farther away from the sun. And so he figured out that if you draw an imaginary line from the planet to the sun, that this imaginary line sweeps out equal areas for any given time interval. And so as long as you keep a consistent time interval, the areas that that line sweeps out is going to be the same for every given time interval. Even though it's faster over here to the left near the sun and slower to the right away from the sun, the area that that imaginary line sweeps out is always constant. So we have Kepler's first law that states that paths of planets are ellipses with the sun at one focus, and the second law states that imaginary line from the sun to a planet sweeps out equal areas with equal time intervals. That brings us to Kepler's third law, and the third law states that the square of the ratio of the periods of any two planets revolving about the sun is equal to the cube of the ratio of their average distances from the sun. And so this is where the math comes into play. Now remember, the period is the time that it takes to revolve around the sun. So one revolution is the period. So say we have two planets here. We have planet A and planet B. So here's planet A, here's planet B. They're at two different distances from the sun, and we're taking their average distance, because remember, if it's an elliptical path, the distances change as they move about their orbit. And so the average distance, if we take the ratio of their average distance, so RA and RB, and the ratio of the time that it takes for one complete orbit for each of them, so one trip all the way around, we find that the square of the ratio of the periods is equal to the cube of the ratio of the distances. And so that is Kepler's third law. This is where the math comes into play here. We have this formula. Let's look at an example problem here. Europa, which is a satellite of Jupiter or a moon of Jupiter, has a period of 3.55 days. So it takes 3.5 days, a little over 3.5 days, for this moon to go all the way around Jupiter. Remember, Jupiter's pretty big, so this thing's moving pretty fast. And we want to know how many units is its radial distance. Now that radial distance, we're talking about the average distance from the planet. So it helps if we sketch the situation or if we just look at what we have given here. So we know that the period of Europa is 3.55 days. And I'm going to give you another little piece here that another moon, Io, is It has a period of 1.8 days and has a radial distance of 4.2 units. Now, what those units are, we don't worry about that right now. But we want to know, what is the radius of Europa given this information? So we have information about one moon, and we notice the period about another moon, and we want to know how far away is this moon. So we use Kepler's third law to solve for the unknown. And our unknown is the Europa distance, which that cubed is going to equal all this other stuff over here. And we plug in our ratio of the periods, make sure we square it, and then we multiply by the units of IO cubed, and we get a radius of 6.6 units. Now the key is we get this 288, but don't forget to take the cube root of that in order to get 6.6 units. So what does this answer mean? Well, it means that Europa has a greater period than Io. So we expect Europa to be farther away from Jupiter than Io is. And so this 6.6 agrees that it's farther away than the 4.2. Well, both of these moons in that last problem and all of the planets around the sun have this force acting on them, and it's the force of gravity. And we see that gravity works throughout the entire universe. And Newton was able to find that the gravity that acted on the stars and the moon and the other planets is the same gravity that acts on Earth. And so he came up with this law of universal gravitation. And so it started with his conclusion in 1666. The date doesn't really matter, but that's when it was. And he concluded that all objects with mass have to have this attractive force. So any object with mass attracts another object with mass. And the force of attraction between these two objects was proportional to the object's masses, so meaning higher mass, higher force, and also, we found that it was proportional to the square of the distance between them. So, obviously, higher mass, higher force, but also higher distance between them, lower force, and lower to the extent of that factor squared. And so Newton came up with this formula through his observations that has that proportionality in it of the two masses and the distance between them squared, and this constant, big G. Now, big G is like baby G in that it's a constant, but the number is completely different. In fact, it's 6.67 times 10 to the negative 11th, and we'll use that number a little more in class. And it's not something you have to memorize, it's something that you may want to write on your formula sheet. So if we take Newton's laws and Kepler's laws and we put them together, we get this really nice simplification. And I know looking at it, you might not think that it's a nice simplification, but in fact it is, in that we can look at the period of a planet orbiting the sun. So any object orbiting the sun, we can find its period just looking at its distance from the sun and the mass of the sun, and of course knowing big G. But big G doesn't change. It doesn't change anywhere in the universe, whereas baby G actually does change. Baby G is dependent upon where you are. So your acceleration due to gravity depends on what planet you're on, and big G, same throughout the entire universe. So if we put the two laws together, Newton's law of universal gravitation and Kepler's third law, we get this nice handy formula. And so we can find the period of any planet orbiting the sun just by its distance, or inversely, by measuring the period, seeing how long it takes to go around the sun once, we can then see how far away it is from the sun. So the last guy we're going to talk about here is Cavendish. And Cavendish had this experiment, and this was back in 1798, so the end of the 18th century, where he had this little apparatus, and he had this rod that had two lead balls on it, and that rod was connected to another support rod that was going vertically and a really thin wire. Now, the importance of this thin wire is that because it was a thin wire, this could move horizontally, and it was very susceptible to any horizontal forces. And so what he decided to do is he wanted to measure big G. He wanted to know what was big G. So he put two really big lead spheres in a fixed position close to this apparatus. So he has these large lead spheres and he has the small lead spheres. And he saw that this thing started to rotate. And so the spheres were attracting the other spheres, and he was able to measure this angle in between. And from that angle, he could calculate the force of the object. And then after calculating the force, he was able to then look at Newton's laws and find the value of big G. So Cavendish's experiment was actually pretty significant in that it was the first experiment to actually measure the value of big G, the value that Newton just theorized about and was able to uh, give a guess on what it was based on planetary motion, whereas Cavendish actually did something in his lab to measure big G. Hopefully after this video you can answer these three essential questions and you have a decent idea of this vocabulary.